It is my pleasure to welcome you to our first panel, The Advance of Digitization in Design. Since Ivan Sutherland's MIT PhD dissertation introduced Sketchpad, a man-made graphical communication system in 1963, the design disciplines have regarded computation with a volatile mix of enthusiasm, hope, skepticism, and fear. In the same year, during the construction of the Sydney Opera House, which was made possible thanks to early finite element analysis, engineers at Arup held a symposium on the use of computers in which they told themselves, the computer can't really take away the act of designing from the architect. The essential thing to remember is that a computer does not possess an imagination. We have seen these debates rehashed continuously in the 6 decades since, coupled with a persistent narrative that the AEC industry is woefully behind in embracing automation compared with other engineering disciplines. If aircraft and automobiles can be designed and optimized algorithmically, why is this approach so elusive for buildings? One answer is that the complex system of the building and the processes that design them are intrinsically unautomatable. In particular, the role of the human seems unavoidably central in our design methods and architecture, not only due to the ego of the architect, which brings a recognizable authorship and a personalized intentionality to the process, but because of the end users of buildings who are people. However, in the face of a rapidly changing climate and a critical need to curb emissions across all sectors, computation again offers compelling paths for a design response if it can be linked with human creativity, nuance, and equity. In particular, the ability to simulate, survey, measure, compare, and generate designs and their context with instantaneous and democratized access to data can amplify human design potential in transformative ways. In recent years, emerging technologies in artificial intelligence, such as deep learning, bring these possibilities tantalizingly close to reality. In today's panel, we will hear from 3 experts in the field who are exploring and advancing these ideas in a variety of exciting ways. It's my pleasure to introduce them to you. First, we have David Martinek, who is the co-founder and CEO of Airworks, where he spearheads the development of Airworks' autonomous drafting technology to advance the application of aerial intelligence and transform the engineering and construction industries. David holds an MBA from Sloan, and Airworks was part of the MIT DesignX 2018 cohort. Kyle Bernhardt is Director of Building Design Strategy at Autodesk, where he leads a business strategy team focused on how technology can help the industry become more sustainable, efficient, and safer. Previous to his current role, Kyle was a longtime member of the Revit and BIM 360 teams, leading project management for BIM 360 design, and he is endlessly curious of how technology can help the AEC community to meet the challenges of tomorrow's Earth. Finally, Joe Paget is Director of Engineering Data Science Product Management at Altair. He comes from an aerospace background and has 2 decades of experience enhancing the design processes with numerical tools, notably optimization and machine learning. He has a particular interest in the integration of these methods into everyday software of designers and engineers. David will start us off with a brief presentation, followed by Kyle and then Joe, and then we'll all join together on the virtual stage for a discussion. David, the floor is yours.
Thanks, Caitlin, and hello, everyone. It's a pleasure to be here today. It's exciting for me to come back full circle to DesignX after we graduated in 2018. And I'm glad to share some updates on what we're working on at Airworks that is very relevant to this exciting topic of computation and design that is being discussed as part of this panel. Now, let me see if I can get my screen up. Excellent. So at Airworks, we intrinsically believe that you can only define the future if you understand the world of tomorrow. And similar to the introduction we've had for the entire event, remote sensing and aerial data of some sorts play an increasing role in that mission. And so ultimately what we do at Airworks is we developed a technology that helps us understand remote sensing and aerial data better and autonomously to be able to make sense of these large data sets in order to be able to then take conclusions and define and develop the future of how the world is supposed to look like. So the theory we have is that basically every building starts with an accurate map, an accurate representation of how the world looks today. The predominant technology that the industry has been using to understand how the world looks like, it's called survey and mapping in some forms. And it's a very accurate representation of a project or a future project mostly in CAD on other similar systems. And to get that kind of data today is very, very complex and time consuming. As you can see on the top right, the predominant technology has been optical based, and more recently, also RTK technology has been used for mostly in the field data collection, which is extremely accurate. And that has always been the challenge for remote sensing in the past, that the accuracies required are very hard to reach. And we're talking here about better than 1/10 of a foot, or even a 20th of a foot of accuracy. Now, however, the advancements that we've already heard in GIS and satellite technology, but also the advancements in sensing and automation that has led to the creation of drones that now produce images that are 5 times more accurate than aircraft images at a fraction of the cost, have led to a massive increase in the use of such technologies. And so has the advancements in LiDAR sensors that are mostly fueled by the autonomous driving industry, that now make it possible to collect point-based data of every project at very high accuracies in the world, either through aerial sensors or through on-the-ground terrestrial laser scanning or mobile mapping. Now, companies have been using this technology more and more over the first couple of years, but it also comes with its challenges. I just want to show you a quick example on how these projects look like. What you're looking at here is a point cloud that is a very standard data set derived by a drone that consists of hundreds of millions of data points. Every point has a color associated to it and also has a GPS coordinate. And we get to a place where every point is about an inch. So you get an inch every point, which leads to hundreds of million points per acre and for every project. Now the question is, how do we use that data, and how do we actually create something that we can use for besides just looking at it? And this is another example, which is a little bit larger. It's an aerial point cloud from a oil refinery that was collected by one of our clients, Aerial Solutions, that is extremely complex and hard to analyze. And these problems essentially have made it very, very difficult for architects and engineers to work with this kind of data. And we always compare it to traditional mapping. That if you were to use traditional survey equipment, it would take you 75 years to survey the city of Boston, more or less, at very high detail. Now, if you wanted to interpret aerial data at the same level of detail, it would take you 38 years to manually interpret all these images in point clouds. So at Airworks, we thought, can we use technology to solve that problem? And we looked to familiar fields, and some of you might have already seen the image here on the top left, which is basically computer vision and machine learning algorithms that of different types that identify, classify, and essentially segment objects in an image and can help us identify and understand what's presented in all that imagery. And most of you have heard of the technology used in self-driving, which is also very similar, right? Through cameras and LiDAR sensors on moving vehicles, can we make sense of the world around us and understand better of how we can autonomously navigate in the environment? And we essentially did the same thing at Airworks. We looked at the type of data that you get from remote sensing equipment here, and we manually, at the beginning, classified that data into the different regions: buildings, vegetation, utilities, the ground truth. And we started to train an AI model back in 2017 in the hopes that ultimately the computer would understand these connections and be able to derive such classification all on its own. And that's basically what we've built now as the core of the Airworks technology. You're now able to throw in a high-resolution orthomosaic or a 3-dimensional point cloud. We can run the same AI models that we've trained with all the past data that Airworks has seen, and we can now autonomously derive a pretty accurate definition of the future that is not only a pretty image, but it actually tells us, how many buildings are on the site, how many trees are on the site, and so on. And today we have, already developed 12 models on our web application with 12 different feature classes, but we're expanding on these feature classes every day. So today we're able to detect buildings, we're able to detect utilities, we're able to create very accurate contour models and any kind of road data as well, vegetation and water bodies, for an example too. An example is here. So this is another input aerial image, and the Airworks algorithm would ultimately bring us to this fully finalized CAD engineering plan that is now ready, either to run analytics on top of it in an automated way for entire states or cities, or to actually go into detailed design and start conceptualizing and building the world of tomorrow. In terms of real advantages for our clients, that means they first of all, they don't need to run this kind of compute on their own computers, so don't have to invest in very complex machinery. But also, we already provide them with 80% cost savings, and today already 3 times faster turnaround times. At scale, we believe we can get up to 100x, 300x on the turnaround time for some of these analytics compared to the human workflow of manually extracting that data. And since we launched last year, we've seen a significant interest in analyzing this data. Most engineering firms have now built their internal teams to collect remote sensing data of any sorts. And what you see here is a map of basically all the projects that they've sent us only in the last 15 months. And you see that we already cover 48 different states. We're still working on South Dakota and New Mexico, but everything else is sort of already represented, and we're expanding that coverage map more and more. But this for us, we think, is only the beginning. Again, we truly believe you can only build the world of tomorrow if you understand the world of today. So we see our technology sort of powering a lot of the decision making that's happening in the AEC space, and also what the other panelists are probably going to talk about. So if you want to understand infrastructure health and allocate maintenance budget on a city level, you first have to understand what's the condition of your assets, both of the highways and roadways that you have, but also the buildings and other assets and bridges that are going on. A lot of people talk about generative design these days, but well, if you want a computer to build any kind of design solutions, the computer first needs to know what's there today in a very detailed manner. And those are the kind of solutions that we can power now with AI and remote sensing. The next example I want to bring up here is HD maps. So a lot of companies believe that in order to power autonomous driving on a national and global scale, the only way to do that is to produce very accurate maps in a recurring manner of our cities and countries. And it's way too expensive to do that the traditional way. It's even way too expensive to do that with mobile mapping. So a lot of people are trying to use AI also in the creation of these maps in order to update the environment in a very detailed manner. So we're excited about where this world leads, the world of automation, the world of AI, and especially in design, and looking forward to speaking more about it with everyone else that will be joining me. Thank you for learning about Airworks, and back to Caitlin.
Thank you so much. Kyle, you're next.
Thank you, Caitlin, and thank you everybody for the audience today. Looking forward to the conversation. Let's get the share going. All righty, cool. Let's get started. So what I wanted to talk with you guys a little bit about to set the context for today's conversation is really around how the job of technology is evolving with the needs for humans to scale. Really, it's a scaling problem that we're working with here. If you just think about some of the core numbers, we're going to have about 10 billion of us on Earth by halfway through the century. About 400,000 people every day joining into the middle class. And these individuals need to have places to live. And so we think about 68% of them are going to need to be in cities by about halfway through the century here. And if we do some basic numbers, we can project out we need to be building about 3,600 more buildings every single day by the midway point to the century. And that's really a problem because there's these key numbers that are nagging at us that we know are there, which is buildings are not particularly efficient. They are designed around initial cost often without as much concern about the long-term life cycle impact to the world. There's a huge amount of overall business loss here. And ultimately, we've got this scaling problem that we're dealing with. And jump back in time about 14 months, the big R word came in around resiliency, as we've seen huge changes to the way in which we design and construct buildings as well as inhabit those buildings. We're seeing shifts towards digitalization. We certainly see it on the Autodesk side of the business, as our users have jumped to the cloud to help maintain collaboration. We're seeing increased focus around how we can create a more resilient built environment. And when we put this into context for how things are typically done, we end up with the reality that, it wasn't that long ago that the design process looked a little bit like this. We may get ourselves to a point today where we have iPads on the job site, but the construction site of today doesn't look that different than this picture. There's 17 cranes in this picture, if you want to count them, but this is a just-in-time delivery on-site fabrication. And so there's a tremendously inefficient way in which we build buildings. Now, we are digitizing this process. This is a great image of a building information model that is capturing the full complexity of the proposed design. but oftentimes this capturing has been made after a lot of the major design decisions are made. This is a modeling process to drive documentation and downstream processes. And that really brings us to the core thesis that we have at Autodesk. And one of our big drivers is that reality that the way in which we design really can't meet this crushing demand that we know is looming on the horizon. Every project is its own special snowflake. The way we analyze things is really decoupled from outcomes. You might want to understand from analysis, maybe the solar heat gain on a facade of the building, but ultimately what you care about is the occupant comfort, the cost of operation, the life cycle cost of the materials that are required to fabricate that building. And when we look at the way the design process carries out, there's a lot of repetitive tasks that could be enhanced via automation. And we like to think about this as part of the shifting role or job of technology. We started with this digitization process where you're capturing the drawings in a digital format and drafting tools like AutoCAD, MicroStation, that sort of thing. With the advent of building information modeling, we really converged the modeling, drafting, and analysis process. As the cloud is rolled out, it's allowed us to collaborate in a much better way. And looking towards the future, we see the introduction of AI as a key facilitator for the changing of the verb that technology is doing in service of these design teams. So technology is no longer capturing, but it's now informing and augmenting those humans. And this is all towards, it's all based around a drive to really shift where the effort is going. For those of you guys who are familiar with the McLeamy curve, well, here's a McLeamy curve. But that thought process around how BIM and really digitization can shift the curve, so to speak, to an earlier state of the project when it's easier to change and less expensive, it hasn't really been thinking all the way forward into that evaluation process. Oftentimes that pre-spend process is one where spreadsheets are driving the process. There's no BIM there. And we see a huge opportunity to really shift the effort curve further to the left, because at the end of the day, this is the only way it's going to work. At the same time, some of these things are deemed constraints. That idea that the ability to change gets harder over time and it gets more expensive. We see AI and design for manufacturing and assembly as key enablers to really shift those curves. And so that's really the core idea of what we're driving right now here at Autodesk. And when we think about that world of an informing technology job, we see new technologies that really help to drive that future. The idea of creating an experience in software based around the outcomes that matter for those design and construction teams, that idea that AI can look across massive data sets and start to deliver insights that no one human could ever do on their own. And then that final idea that you could have technology helping you do a better design output in the design experience itself. And when we talk about this, usually most people start to think about the picture on the left-hand side here, which is the idea that we're building this sentient AI that will take over the world. But really what we think we need to build here is that Iron Man suit that can propel humans to go do things that they couldn't do before. And when I think about that intersection of technology and humans, there's no better example than AlphaGo. And so there's two key takeaways from a few years back when AlphaGo played Lee Thibodeau in a game of Go. And I want to show two key clips from a wonderful documentary that really illustrate this point around technology and humans.
와, 정말.
That's a very surprising move.
I thought it was a mistake.
When I see this move, for me, it's just a big shock. What? Normally, human will never play this one because it's bad. It's just bad. We don't know why. It's bad.
Yeah, that's an exciting move. I think we've seen an original move here. That's the kind of move that you play Go for.
And it was an amazing move. It turned out to shift the game. The calculation was that a human would play that move 1 in 10,000 times. And AlphaGo went on to win the first 3 matches. And on the 4th match, there was a pivotal moment from Lee Thibodeau, move 78. And let's watch that.
This is the hinge of the game.
Oh, look at that move. That's an exciting move.
Look, basically,
Oh, he found the wedge.
Whoa.
It's going to change the equation because now black cannot escape.
That would be so cool if that works.
And it did work. He went on to win that match, the one match that beat AlphaGo. But this is a perfect example of how humans are incredibly creative, and coupling that together with the power of AI can really drive humans to do great things. And this is something that we've been working on very deeply at Autodesk. This is an illustration of some really impressive computational design that helped to drive the interior design of Autodesk's office in Toronto. And this is an amazing illustration of technology, but the yucky story underneath was that this is a bespoke AI that was really targeted for a particular example. And really what we've been working on is democratizing that ability to run automation to help professionals. This is capabilities in more recent versions of Revit that allows users to do building massing optimization. So this is something that we're working on to really bring that out to the end user. And what they're telling us as we go through this process is it really needs to be this symbiotic relationship between the end user and the technology to drive better outcomes. This is an example from our CTO's office working around structural analysis, and we're using AI to drive the structural design of beams. So we're moving through a flow where the human and the technology are working very smoothly together, validating that in an analysis, setting up constraints, and ultimately optimizing the end result. So this is the trajectory we see ourselves on, moving towards that more democratized AI experience to really help the users. Which brings us to SpaceMaker, which is a new addition to the Autodesk portfolio. This is a tool that's designed for the earliest stages of design processing, where you can bring in massive data sets to understand the urban context. The end user can work bidirectionally with that AI, generating potentially thousands of options and comparing the impacts of them, delivering in-context, real-time, artificial intelligence-driven analysis. And so this sort of capability is really technology rising to that occasion to be able to deliver a better design output. And when we think about those future design tools, they look, whoops, one step too far. They look a little bit different than what we've been seeing historically. We've got automated data available. We've got AI on your shoulder to help. We've got real-time analysis to understand the outcomes. And that idea that it takes a village is really a first order principle. And so together, those are all those key trends that we see as a huge influencer towards that shifting of the role of technology. Caitlin, back to you.
Excellent. Thank you so much, Kyle. Joe, you're our final speaker.
Okay, thank you. Can you hear me? Excellent. Let me share my presentation. Okay, so this should play off nicely from the previous presentations in a nice flow. So Altera's, oops, let me get rid of my, my Zoom in my way. Altera's vision is to help people combine simulation, high performance computing, and artificial intelligence into one area. So Altera started off 35 years ago with mostly out of an automotive background, but they've moved into many industries. Some may be surprising, like financial services that are very different from where we started, but also plenty of background in architectural and civil companies as well. But every company has to start somewhere. And as I mentioned, we started as a simulation company. So believing that simulation would drive the design in the long run, right? Not something that's done after the fact, but something that is done a priori. And as simulation gained more traction, it simply needed more high performance computing. So moving into queuing systems, right? The server racks of yesterday are slowly moving into today's cloud systems. And as you generate all this data, what are you going to do with it? As we've heard before, the human mind is only capable of processing so much. So this is where the data science, the machine learning, the artificial intelligence comes in, and the convergence of all these ideas into how they will drive design. So what do we mean by simulation? Well, honestly, it's much cheaper to crash a car on a computer virtually and make design changes than it is to do it in the real world. Doing that, you can do more than simply structures, more than automotive. You can make the world a more efficient place. You know, even down to the factory floor, increasing efficiency wherever we can. But even then, it's not just single point design. Something like optimization, topology optimization. Here we see OptiStruct, an Altair product from the mid-90s, making suggestions as to how to design a structure. And it's not just about the technology. So technology is only as good as how well it's integrated into the process. So you can see here the steps from the left to right. All this has to be handled and presented to the user as part of the process. It's not enough just to have great tech. We want everybody to be able to use it. And of course, it's not just about structures, it's about anything you can simulate. At Altair, we are constantly reminding each other you can simulate anything. You can simulate structures, you can simulate flow through a city, electromagnetics, everything is capable of being simulated. And that means everything is capable of generating data. Now you have these two different disciplines, engineering and design, right? Many of us go to school for that topic. And we've also seen in the last decade, there are plenty of people going to school just for data science, right? They learn machine learning algorithms and they become experts in that. But in reality, we need this hybrid space, this space in between. And at Altair, we've coined the term engineering data science within our own company. And it is the engineer who knows about neural networks just as much as it is the data scientist who wants to learn about engines. So it's an interdisciplinary hybrid application. And where does our value coming from? Well, sort of what we've heard from the other panelists as well. Machine learning can be applied to data science to reduce repetitive, tedious tasks and honestly let the engineers be engineers. I come from the simulation background. I didn't go to school for all these years to mesh finite element models, right? My actual expertise is in interpreting them. So the last thing I want to do here with the few minutes that we have before we move on to the panel is to go over some examples, two examples specifically of how we're trying to integrate these types of technologies into the everyday user experience. So the first one is an example about working with geometries. I sort of love this story. I have young children. If I poured out all my children's Legos onto the table and asked them to put them in piles of similar shapes, it's something even a young child could do. But if we started to try to write rules to do this with computers, it gets complicated, right? Our first attempt may be, say, take everything with 4 pegs and put it in a pile. And that will quickly run into problems when we realize a 4x1 geometry doesn't quite have the same shape as a 2x2 geometry, despite both having 4 pegs. We could then get into maybe rules and ratios of volume to area, but we're starting to get into what machine learning folks would call feature engineering. And what you really want is automatic feature engineering, to be able to look at a geometry and automatically extract features from it. If you can do this, you can now perform operations that humans do somewhat easily, like search, grouping, forming automatic sets of similar shapes, or even classification, identifying what a part is. And with this, you can layer automation on top of it. So here there's a simple video that plays of an airplane wing. And what the user experience looks like in real time. They simply select the assembly and ask it to match. And this is going to create self-forming groups. So as soon as this runs, it's only a handful of seconds. We'll see some new assembly structures start to appear of similar shapes. And the video will scroll through a couple of them. You'll see how quickly it could form, put similar shapes together, even if they're in different orientations and alignments. And this is something that, yes, absolutely a human could do. It may take a human 5, 10 minutes, 10 minutes to do what I did on the screen, but it literally here was cut down to seconds. Another example is taking all these simulations that we can do and actually learning from them. As a company, if you've run these simulations year over year, can you learn from what you've done in the past to predict future behavior? So this idea will work as well, equally as well with a parametric design. So a small bracket that you see here that has a lot of choices that go into the design. From either geometric dimensions to material choices. But the same idea would work just as well with brackets that share no common parametric basis. The idea is you want to throw everything at the machine and have it learn and then be able to make inferences in the future. And those inferences should not be limited to just sort of KPIs or scalar predictions. We're also looking at being able to predict the entirety of the physics in and of itself. So the same idea here in a quick video. On the left-hand side, you have some sliders that correspond to design changes. In this case, they're parametric variations of the thickness. And on the right, there's a prediction of a full physics simulation. This happens to be a crash event from an automotive crash, so smashing that car into the wall again virtually. And this type of analysis could easily take 10, 15 minutes in a computer. If you did a full vehicle, it could take hours, but now you'll have real-time predictions of the behavior. So faster turnaround for engineers to make those decisions and be engineers. So what we're doing at Altair is trying to combine those 3 ideas, the power of the AI, the power of simulation, to take your data and make better decisions as part of it. So that's all I have today. Back to you, Caitlin.
Excellent. Thank you, Joe, and thank you to all of the speakers. And those were all super inspiring and thought-provoking presentations. Are we all here on the screen? Is it Is it a good time to start? Excellent. All right, so in the next 28 minutes or so, I thought we could just have a bit of a discussion following up on some of the themes that all of you brought up, and really eager to hear more from all of you because you're all working on such exciting things. Maybe I'll start with something a little more a softer question, and we can get into some more technical questions. I'm interested in particular, a lot of you talked about artificial intelligence and deep learning and kind of new potential that we're at this moment in time. However, on the other hand, I think we've been here, if you look through history, people have been talking about the power of computers to empower generative design, for example, since the 1960s. The earliest structural optimization methods were actually called structural synthesis, getting at the idea that the computer could somehow generate a structure. And those, of course, were for aerospace applications. But I'm curious, in all of your experiences and in your opinions, what is it specific about right now, about 2021, in terms of our challenges and our opportunities that you think really are changing the way that we think about design and construction, thanks to these emerging technologies in a more profound way, if anything? And, happy to go in whatever order you like, so please just unmute yourself and speak.
Yeah, Caitlin, I can talk to this a little bit. I think we have a couple of different items coming together at the same time, especially as it pertains to AirWorks, but I think also the other industries or the other companies represented here. One element is definitely compute power, right? So we've just seen Moore's law is, I think, still applicable, and we've just seen a massive increase in compute power recently, in a way that the data sets we're looking at now of like hundreds of terabytes at once weren't handleable. Like no one could deal with that just like 5 to 10 years ago, essentially, right? So that enables a much broader application to AI, frankly, right? That suddenly makes it possible to use that data at scale, right? And part of that is also GPUs have increased massively, right? So everything that's vision ultimately has been enabled by the increase of GPUs and the technology that are available there, and that just makes it a lot easier. The second element to us is really sensing, right? And the quick availability of data, frankly, that has also not been really the case across the globe, right? So, for example, drones are only here since 5 years or so in a commoditized fashion, and these drones carry sensors, they carry cameras, they carry LiDAR sensors, and those are not always developed because of the built environment or driven by the built environment, right? Often it's other industries that are sometimes better funded that drive the advancements. For example, self-driving cars have powered in a massive way the abilities for sensing that we can now apply also to the built environment, right? So interdisciplinary collaboration becomes a lot more important, and for us, it's these two things, right? Compute and basically data availability from an engineering standpoint. I know there's probably other people that can talk about the need basis, and we can dive into that.
Thank you, Kyle or Joe.
I'll take a stab at that. Thank you, Caitlin. Great question to start with, by the way. So to me, I'd start with the big differentiation now is the tech stack we're building on. And there's really 3 things that I would put in there to illustrate that. Thing one is the scale of cloud computing, as David was mentioning, is really just making it possible to do compute at a scale that you really just couldn't do. A lot of the cases, it's not that the algorithm has been missing. I mean, if you look at machine learning, most of the primary algorithms have been built for over a decade now. The difference is you can train a model in a much more fiscally viable way than you ever could. So just kind of scale of compute. Number 2, I'd say just the reality that the internet is connecting us. And specific to the built environment, that really gets to the heart of the problem that so much of this optimization spans contractual responsibilities on a typical job. And when you've got a single user working inside of their network and they're running their algorithm, the scale or the scope of the things they can simulate is limited to what they can touch, because the people on the other side of that contract boundary don't have visibility in there. They don't want people messing with their contract responsibilities. But with the cloud, you can really connect teams and think about going bigger with the goals of the algorithm. And then the final piece that I would say is we've just gotten better at making software. I mean, I don't think many people can talk about amazingly well-designed, beautiful pieces of technology that can help them do the design process from 20 years ago. We've learned a lot in the last 10 years via mobile design, the progression of the user experience practice as a whole. And that's really empowering us to deliver things that are much more democratized. It's not so much that the abilities haven't been around, it's the ability for everybody to do them that's been the problem. We've got these, keynote speeches and on conferences that I go to where it's amazing things, but it's like 3 people on earth know how that works. And we need to be able to make it so that hundreds of thousands can have access. So those are the 3 key things to me that are really making today different than yesterday.
Thank you. Joe?
I don't know that I can add too much more to what is said, beyond computing power and sharing of information, right? Essentially scale. But the one piece I'll add is just simply sheer time. And I guess this is a variation of Kyle's point. I'm too young to remember when FEA, came onto the scene, say in the 60s or 70s, but I suspect it was rejected by the sort of establishment engineers who said, that's just voodoo black magic. However, I was old enough for the world when optimization came on the scene 15, 20 years ago. And the people who were FEA analysts said that's, voodoo black magic. But when we would come back with results faster than they could, it became accepted. And I believe some of the artificial intelligence stuff maybe is going through the same sort of growing spurts, which is 5, 10 years ago, it was seen as voodoo black magic. But as you start to see it proven out, nothing changes people's minds like success.
Great. Picking up on that, I think a lot of you mentioned scale, but also data. And I'm curious about that. I think probably all of you showed examples of supervised learning in your work, which of course requires labeled training data to operate on, meaning you need to have data of the type that you're trying to work with, and you need to know enough about the data to train a model. Now, in other learning applications, data is ubiquitous, and I think that was maybe another reason that the field has advanced so far is in other industries, we have so much data that learning methods have been really developed incredibly rapidly. But for example, like the MNIST data set, which is a data set of hand-drawn digits 0 through 9, I think there are 300,000 images in that data set, and that's a pretty small data set compared to some that people operate on. I think it's probably harder in the buildings world to get data sets, especially labeled data sets that are that large. What are your strategies, or what do you see as the best ways forward to deal with this relative data scarcity problem?
I can start off with that. When we first started looking at data science projects a few years ago, we sort of, well, I want to use the term bifurcated, but there was actually 3 topics. So I'll say trifurcated, I'll make up a word, into 3 different groups. So we had data in hand, and those are the types of projects that you can almost take what you have like it's an Excel sheet, right? Oftentimes they're in relational databases, but they're perhaps what people think about as conventional machine learning applications. On the other side, also more and more commonly seen, you have data streaming. So data on the fly, data coming in, maybe sensor monitoring, things like that. But we had this third class, especially with our interest in simulation, which was data that is going to be synthesized into existence, data that I do not have, but I will make synthetically. And we simply refer to that as data on demand. So we had data in hand, data on the fly, and data on demand. So that's one solution to the problem.
I actually like this a lot, Joe, and maybe we should talk more about it. If you can produce some synthetic data for us, we're in business. It's that would be phenomenal. No, but essentially, I mean, what we tremendously believe in at AirWorks is that no player in the world can do it alone, right? So no one in this world has enough data by themselves in their own corner, in their own company, in their own office, to build an AI algorithm that works in all scenarios, right? And that's why, like, we intrinsically focus on collaboration, and I think a lot of other more successful companies in this world do as well. I mean, if we look again at the example Tesla, now there may be some debate if vision is enough to power autonomous cars, but the concept is let's get everyone involved. Let's produce enough value so my product is interesting. But then let's get everyone involved to collect more data and essentially make that product better. And at the same time, give some of the benefits back to the client in terms of lower acquisition price and lower and better value to the customers, right? So I think that's a lot about how we think about data. How can people in industries collaborate around these decisions on one data set, but maybe even multiple data sets, right? How can decisions be passed around between different players in the industry? So integration, collaboration is, I think, the world of the century now.
Yeah, just to build on what David and Joe said, I mean, there's no shortage of data these days sitting on hard drives and network storage, or even up in the cloud. As you mentioned, Caitlin, the challenge is one of structuring that information, especially in a consistent way We have drawings as a consistent output of this process, but you've smashed down so much of the intelligence that would have come from a building information model. But sitting under that building information model could be a completely divergent set of metadata standards that help you understand that design or that construction intent. And so driving towards more consistent implementation of the digitization of the process is going to be a huge enabler for a lot of the more advanced machine learning capabilities. But that doesn't mean that there isn't great data that's available today. One of the things we've learned at Autodesk is the need for extreme transparency about what's going to be done around machine learning, because most people tend to kind of freak out on face value about the idea of leveraging information to drive machine learning. We have a product in our portfolio called Construction IQ that helps to understand where risk exists on your construction site on any given day. And what's interesting about that application is that it's really running on two different underlying data sets, both the idea of what the issues are that have been logged on different parts of the job on any given day and assimilating that, but also the workflow data that allows understanding of this person passing it to this person. And, oh, this person seems to have a cluster of issues that other people aren't having. And so that's that relationship chain. But as we've pursued that, we've understood that we need explicit consent. So for example, our Construction IQ product, our standard terms of use would preclude our use of any of that information for driving a machine learning model, which is why we actually have an explicit separate consent required if you actually want that information to be part of that overall AI. And overall, this is an area there's a huge amount of discussion on, and it's something that we have to get right, because ultimately we're never going to get to those trained models with the efficacy that we need and the speed without that scale. But at the same time, baked into those work products, that's the institutional knowledge of some of the greatest firms on earth. And they're not exactly ready to help their competitor down the street with the benefit there. And so it's just something we have to get right as an industry.
Yeah, that's a super interesting point. I was going to ask something exactly about that. Basically, yeah, this there's a lot of ethical questions, obviously, that come up with human-generated data, and especially because it's related not only to these these people and firms' livelihoods, but also in some ways, it's their artistic expression and their personal expression as authors. And so the idea that would then somehow be consolidated or crowdsourced in order to produce to produce new generative models and tools raises important questions, I think. Another thing that I often see is that different designers or different firms also want to differentiate themselves stylistically. And I think that's true in architecture, but it's also true in a lot of other disciplines. And the idea that like automation could be seen as a way to avoid that kind of differentiation, that suddenly everyone is converging towards the same thing. And if everyone has the same tools, will we all have the same sneaker, or we'll all have the same skyscraper? Is that a problem? Because you said, I forget which one of you said it's a problem that every building is bespoke, and actually we should be moving towards more standardization. So do you think it's a problem that we want to maintain sort of individuality in the output of AEC? And if it is a problem, how do we handle that?
So Caitlin, I was the one who said every product is its own snowflake. So I'm probably the first person to dive into that one. I personally don't see it a problem if we move towards a more productized supply chain for the built environment. There's just no way to make a macro shift in the way in which we build buildings than to move towards that more industrialized, productized view around how these buildings are constructed. At the end of the day, you can build some amazing thing with Lego blocks, but there's still Lego blocks under the hood, and there's still standard interfaces, there's still standard sizes. And to me, that's the trajectory we need to get on. As much as we would all like to have our own custom Lego blocks, at the end of the day, there's a massive overall cost to the industry by taking that fundamental approach. So it's kind of, we want to move towards Legos, and you can still do amazing things with Legos.
David or Joe?
Yeah, I mean, this is more a personal opinion than an educated thought here, but to me, the question is always, what does the market reward, right? Ultimately, everything is a question of market economics and demand and supply. And so far, like people don't get rewarded for too much standardization, right? The most valuable buildings in the world are those that have been designed in some unique and creative way, because people appreciate that kind of unique living space and creativity in some ways, right? So as long as I think we preserve that as a human, we're like, creativity is what we add to the process and not necessarily the laborious, fundamental physics of construction, I think we're in a good spot and we'll still see creativity in the building process.
So one thing I'll add, going back to Caitlin's remarks about do you have convergence of design? I think in some ways you will see it. And the example I typically bring up is automobiles. If you go back, at least in my mind, 40 or 50 years, cars on the road look very unique. Now they all more or less look the same. But that's because they have common requirements. A car on the road still doesn't look like a race car. And the environmental conditions that are driving it are basically what's driving the optimization problem. A sort of very formative story that I can share here is the first time I ever took an optimization class. The professor shared an advertisement in the paper, and I believe it was for a dishwasher, and said the advertisement said optimize. He asked the class, does anyone have an issue with this advertising? And of course, it all seemed normal to us. And he pointed out, optimized for what? Optimized for efficiency, optimized for cost. Until you pose that optimization problem mathematically, you haven't narrowed down what you'll get out. So as long as you're putting different requirements on the system, you'll have different outcomes coming out. And in architecture, although it's not my background, perhaps collecting data and deciding how the building needs to be designed for wind loads, or the underlying structure would lead to different design. So unless you're posing the exact same problem, I don't believe you will actually have a singularity.
My sense is that the biggest challenge in using automation and algorithmic thinking in design is formulating the problem, formulating the objective function. It's a really wicked problem. There's so many competing things we care about. There are time scales that to be considered. It's a really, really tricky thing to do. And so, yeah, I share the sense that different firms would do that differently. Maybe related to that, I wanted to bring up the question of sustainability and climate change, since I think that's also on all of our minds, and we heard from that at the beginning of the symposium. In particular, I think, Kyle, you showed the impact that buildings have. It's about 40% of emissions globally are due to the built environment. Some of that is due to the energy used to operate buildings. Another large percentage is due to the energy and emissions associated with constructing buildings. Automation is sometimes promoted as a way to combat that, or even to adapt to the changing climate. Are you seeing any of this in any of your work? How are you trying to engage with climate change and sustainability? And how do you think our future built environment should respond to that?
Well, you said my name again, so I'll start on this one. I mean, well, for Autodesk, it's pretty core to what we're trying to accomplish. As a human on Earth, with kids, and they'll have hopefully I have grandkids eventually. This is the world we're giving them. And when I think about what we need to do there, it's really all about up-leveling the built environment's impact in the design process to really to be promoted to the same level as the economic function. Because right now, the economic function is driving that. There are so many buildings that are developed by a certain individual who immediately sells it or sells it within 2 years. And then they've got renters that are picking up the utility cost. So there's really a financial disincentive in a lot of scenarios. It's almost better economics, if you look at it in a completely selfish way, to go deliver a not particularly efficient built environment. And that's the challenge overall, is we need to be able to expose the economics of these decisions through that design process. That's something that I'm really excited about as we think about partnering with some of the bigger firms on Earth. They're coming to us saying, hey, look, we want to be able to promote this consideration, because it's not like our owner doesn't care about this. It's that they make these big financial decisions at the beginning of the project. We make these big form decisions. And right now, our design tools, the only time we can get the energy use intensity out of them, a core metric is once you've done this detailed BIM authoring process. So that ability to get that insight in an earlier phase should really help to promote that. Because at the end of the day, there's no way out of this without up-leveling those outcomes into the same conversation that are driving the decisions that are currently cost-driven and time-driven. And in the absence of that, you're kind of running on altruism of the individuals involved in the process to try to, quote unquote, do the right thing. But on aggregate at a global scale, you can do the economically feasible thing when all of a sudden you have a clear understanding of the life cycle cost of that building. But today, the challenge is that information comes way too late in the process to have the influence and optimization that's really needed to drive bigger outcomes.
Yeah, maybe to add to that, I mean, I love the economic aspect of the building cycle here, right? And about the incentives in the process. The other thing to think about is really the waste that is created throughout the entire life cycle of a building, right? And a project, right? I mean, we're doing things over and over and over again because every firm lives in their kind of unique individuum and doesn't want to share and collaborate with other players in the market, right? And it starts with things as simple as CAD drawings, right? When we look at, my first question by starting Airworks to people that have been in this industry for way longer than I have was like, why does this information not live out there? Why can't you not just download a drawing of the world somewhere and just reuse it? And I mean, it comes down to like, GIS has been invented only, 20, 30 years ago, and it wasn't used in the industry until very recently, right? So we don't have GIS coordinates of our projects right now, right? And if you would now go get them, you would spend the next 10 years in court, right? So that's why every firm has been very secretive still of their drawings, and no one is really sharing until also the government maybe makes an incentive of like not relying on paper plans anymore. But why don't we build digital databases that can somewhat maintain that information so that we don't have to go get it over and over again? Because when you talk about sustainability, it's not just the building materials, but also how many cars and trucks do we use to build the building? How many aircrafts do we use to get the data, right? Like it's all about the entire workflow here, right? So collaboration brings efficiency.
Yeah, to play off the same ideas, I was always taught that, at least in engineering, there's a traditional V curve, right? You have the design process and then the operational process. And I think what we see with a lot of this data is, if I can try to draw badly with my fingers, rather than a V process, you actually can have a triangle process, right? You can have a feedback loop of this operational data coming back in and driving the design, either the next generation of a design, maybe the next building you build, or even maybe retrofitting, right? Things that you would call maintenance, either predicting it happening or retrofitting a bridge. But bringing all those pieces together, I think from a design perspective, really requires you to know what you want, right? I always try to think of these data-driven processes as a little bit backwards. Looking at a problem, right? And I think this is a little bit of the Design Next ethos, is you want to solve a problem in the world. And then you have to work your way backwards and say, if I could solve that problem, what data would I need? And then if that's the data I need, how do I get it? And this maybe starts getting into things like, Internet of Things, IoT, Industry 4.0. You have to collect that data, collect those systems all in one environment right from the beginning of the design process. And having a unified system, say like we have at Altair called SmartWorks, where you can collect all this data and both design the parts in a conventional engineering, but also design this IoT aspect of it as well. All this stuff has to play together in a giant loop.
Well, we just have a few more minutes, so I'm going to just ask one last question for everyone to finish up. I'm picking up on what a lot of you said. A lot of you said basically we've had algorithms for a long time, but things have changed over the last few years in terms of compute power and software engineering and interfaces, and we're sort of getting towards the gap of making these tools really for everyone. And I think we still see a lot of hesitancy in the field. I think right now we're the four of us are in a lot of agreement, but when I talk to students, when I talk to practitioners, I do hear a lot of hesitancy about automation for a number of reasons. And so I'm curious for each of you, can you give an example of a strong, compelling critique of automation that you see in your work and a response to that? So what are the critiques that we should be aware of and how should we respond to them? Sorry, that's a hard question to end on.
I can maybe start with the first one. This goes back to an anecdotal I told earlier. But when we first started using optimization in projects 15 or 20 years ago, there was a lot of resistance because people thought they were going to lose their job to the computer. I don't think that's true. I think the AI of the future, at least the foreseeable future before folks like us retire, is less Kyle's Iron Man vision. So I agree with him there, and more the Microsoft paperclip. If you try to anthropomorphize it, it's pretty modest. It's not threatening anyone's job. It works in combination with the humans. Just makes them more efficient.
I always thought Clippy got a bad rap because of the graphics intensity rather than the functionality.
Right.
Sorry, Kyle or David?
Yeah, I mean, in our business at Airworks, I think we've seen this play out over the last couple of years. When aerial data came in and drones came in, especially, and laser scanners came in, now everyone thinks they're surveyors and they can go out and, you fly a $2,000 drone over a site and produce, just because your resolution is at 1 centimeter, your data is going to be at 1 centimeter, right? And just blindly trust that data. And so obviously there was a big pushback, very rightly so, from the industry to say, look, wait a minute, like this is not certified practice. And we have to be very careful because of the financial implications of any wrong decisions and any bad data out there, right? And I think that this is still playing out, but we're starting to see rules around automation and AI in the context of some of these applications. And that is, I think, very useful. And companies like ours, we love this kind of transparency and like, what can different players do and can't, because then we collaborate with these professionals, right? Basically, we try to see our life as we help them to make, maybe the parts that are not as pleasant of their job suck a little less, but then really focus on the creativity, the professionalism, and the experience that they bring to the project, right? And I think this is when you get a lot of buy-in from professionals if the thing is approached like that. But yes, we have to still have that discussion in society, because again, there's a lot of people that think automation is going to solve everything from day one to the other.
So I'm going to build on what Joe mentioned, because to me, the critique is really the Terminator versus Iron Man thought process. And there's this idea that we're going to create this single generalized AI that knows how to design and construct buildings, but the truth is that doesn't work for traditional standards of care, for licensure, for legal responsibility, insurance bonding. It's always going to take a village to design and construct the built environment. And so we have to think about that idea that we're really creating a number of specialized AI routines that, when combined with humans and great interfaces, can propel them to do things that they couldn't do before. We as an industry kind of started with this a little off. Some of the things Autodesk included, we started out with is like, hey, here it's going to do everything for you. There's actually a great case study from WeWork that's actually a literary study that went into this and explored this idea. They had generated this amazing AI to do optimization of the interiors. And all the designers are like, no, I don't get to actually touch this thing. It's just a big black box. I don't want to do that. That's not how I design. So it's like, oh my gosh, we have to sit down and rethink how technology interfaces with the human design process. And so we see that now playing out with any number of tools on Earth, not just Autodesk ones, that are really exploring that idea of interactive design assistance versus that sentient AI. And I think that's really going to be the path forward for the industry.
Excellent. Well, that's a wonderful comment to end on, I think. David and Kyle and Joe, thank you all so much again for joining us for this first panel. Looking forward to seeing you in person at some point, I hope.